Hello everyone and welcome to the 15th and final logic lecture of Comp 0003. In today's lecture I want to do two things. Firstly, we're going to finish the material on modal logic. So I'll briefly recap where we got to in the last two lectures, and then I'm going to say a little bit more about the correspondence between axioms of modal logic, or the formulas which are valid in a frame, and various kind of mathematical conditions on those frames. And the second thing that I want to do is maybe just kind of give you some idea of what you should be doing to prepare for the examination when it comes. I'll review what have been the main topics of the course and maybe try and give you a couple of revision tips or something like that. So without any further ado, let's go straight to the slides and I'll see you back here in a while. Alright, so to begin with, I'm going to recap very briefly the material that we've seen in the last two lectures. First of all, the syntax of modal logic is exactly like the syntax of propositional logic, except that we also allow the two unary modalities, diamond and box. So the atomic formulas of propositions, we have the propositional connectives as usual, and we also have that if A is a formula, then so is diamond A and so is box A. Diamond A is usually interpreted as meaning it is possible that A, and box A is interpreted as something like it is necessary that A. We can also remember from the semantics that diamond A means A holds in at least one world accessible from the current one, and box A means that A holds in all worlds accessible from the current one. And you can also think of it in those terms. So semantically, we work with frames, which are essentially directed graphs. A frame consists of a non-empty set of worlds, which we can think of as being vertices of a graph. And R, which is called the accessibility relation, is a binary relation on worlds. So in other words, it is a set of pairs of worlds, which is exactly like edges in a graph, where edges are represented as a set of pairs of vertices. And then in a frame, we'd usually think that any particular proposition might be either true or false at any given world in that frame. So a valuation for a frame is a function that maps proposition letters to sets of worlds. So for any proposition letter, the valuation returns a set of worlds when applied to that proposition letter, and it's supposed to be the set of worlds at which that proposition is true. Now, just to make that a bit more concrete, we then have this satisfaction relation. So we suppose we've picked a frame, M, and a valuation rho. And then this notation here means that the formula A is true at the world W in the frame M and under the valuation rho. Again, the satisfaction relation is given inductively. The proposition letter P is true at W, just in case W is a member of the set of worlds obtained by applying the valuation rho to the letter P. So P is true at W if and only if W is in the valuation of P. Then we have all the usual clauses for the propositional connectives. So W makes not A true if and only if it does not make A true. And it would make, let's do another one, let's do implication. It would make an implication A implies B true if and only if it makes A true, then it makes B true. So that's all just kind of standard. And then for the modalities, we actually use the accessibility relation in the frame. So W makes diamond A true if there is at least one world, W prime, which is accessible from the current one, which is to say that W prime holds, and W prime makes A true. So A is true at the world W prime. Dually, the formula box A is true at W if A is true at all worlds accessible from W. So for all W prime, such that W prime holds, so that's for all worlds accessible from W, then again, A is true at that W prime. So then we have the notion of a formula being valid. in a particular frame. So if we've chosen a frame, we say that the formula A is valid in that frame if it is made true at all points in the world, at all worlds in the frame, I should say. So M, W, and rho make A true, and that's for all worlds in the frame, and also under all possible valuations of the propositional variables. And, oh yeah, and a formula is said simply to be valid if it's valid in all frames. And we've seen some examples already, I think, of formulas that are valid, and of formulas that are not generally valid but might be valid in particular frames, and things like that. Although it's not on this slide, I should also mention we have the notion of being satisfiable. So a formula is satisfiable if it's satisfiable in some frame, and it's satisfiable in a frame if there's at least some way of making it true in that frame, which is to say there is some valuation and some world W in the model such that the formula becomes true at that world and under that valuation. Okay, so just getting up to what we saw in the last lecture, remember that we saw that we considered the formula box A implies A, which says that if A is necessary, then it is true. Or another way to think of it is, if A is true at all accessible worlds from the current one, then it is true at the current world as well. And we saw that that is a valid formula in a given frame M, if and only if that frame is reflexive. Reflexive meaning that the accessibility relation is reflexive in that every world is accessible from itself. So there are many examples, by the way, of reflexive relations in mathematics. A simple one would be the equality relation. So we take the relation of two things being equal. That is a reflexive relation in that every point is related to itself. If we think of it being numbers, of course, every number is equal to itself. And there are also kind of weaker reflexive relations, such as the relation of being less than or equal to yourself. So, less than or equal. So, of course, every number is also less than or equal to itself, and so that's a reflexive relation as well. So, because these conditions are equivalent, then there's no difference at all between taking box A implies A to be an axiom, something which is always true, like the law of excluded middle or something like that, or just saying that imposing the condition on our frames that they must be reflexive. Of course, those two things are exactly equivalent. And it's not just reflexivity that we can define this way. We can also define many other conditions on frames by modal logic formulas. Although there's also quite a lot of conditions that can't be defined. For example, try to write down a modal formula which is valid in a frame if and only if that frame has infinitely many possible worlds. I think you will find that you cannot do that. So let's go and look at another example now. Okay, so here we have a different condition on frames, which is also a very well-known one, called transitivity. So transitivity says that if y is accessible from x and z is accessible from y, then z itself, it must be accessible from x as well. So this is a very kind of common property. So it kind of says that one way of thinking about it is that anything you can get to in 2 steps, you can also get to in 1 step. And therefore, for the same reason, anything you can get to in 3, 4, 5, or any finite number of steps, you must be able to get to in 1 step as well, for exactly the same reason. Again, you can think of lots of examples of transitive relations in mathematics. Equality is definitely transitive, for example, and less than or greater than or less than or equal to, these are transitive relations as well. And as before, we say that a frame is a transitive frame to mean that the underlying accessibility relation R is transitive. So there's no difference between saying a frame is transitive and that the relation is transitive. It's just a shorthand. So now think about this formula. Box A implies box A. Now this kind of says if A is necessary, then it's necessary that it's necessary. Necessarily A implies necessarily A. And again, that sort of seems like a not completely unreasonable principle that you might philosophically want to have in your modal logic. And we're going to see over the next few slides that the validity of this formula in a frame is exactly equivalent to the frame being transitive. So as before, there are kind of two parts to that. One, we have to show that if the formula is valid, then if the frame is transitive, then this formula is valid. So this formula is valid in every transitive frame. So to prove this, we're going to assume that M is a transitive frame, and we have to show that the formula box A implies box A must then be valid in that arbitrary transitive frame. And of course, for it to be valid in the frame means it has to be valid at all worlds in the frame and under all valuations. So we'll just pick some random valuation row. We won't assume anything about that, and we'll pick an arbitrary world in the model, and we're supposed to show that that at that world W, box A implies box A is true. And of course, to show that an implication is true, we just assume the left-hand side and we have to show the right-hand side. So we're going to assume that box A is true at W, and I'm going to label that as assumption number 1. And then we have to show that the formula box A must be true at W as well. So remember that box A basically says that A is true at everything accessible from W, and box A says that everything is A is true at all worlds accessible in 2 steps from W, essentially. And so we're going to work on that, and we're going to start by simplifying the goal. So remember, what we have to show. We've got that W satisfies box A. We have to show that it satisfies box A. And that means that we have to, roughly speaking, it will mean that we'll assume that something is accessible in 2 steps from W, and we're going to have to show that A holds there. But let's do this, by the book and using the satisfaction relation. So to show that box A is true at W, we have to assume that W prime is accessible from W, so we'll move 1 step away from W to W prime, and we have to show that box A is true at W prime. And in turn, for the same reason, that means that we'll assume that W double prime is accessible from W prime, so R W prime W double prime. We have to show that W double prime satisfies A. So in other words, we've got something which is accessible from W in 2 steps, and we have to show that A is satisfied there. Now, since we have that W double prime is accessible in 2 steps from W, so we have R W W prime, 1 step, and R W prime W double prime, 2 steps. So that means, since the frame is transitive, we remember transitivity says anything you can get to in 2 steps, you can get to in 1 step. So since we can get from W to W double prime in 2 steps, by transitivity you can get there in 1 step, and so we must have that R W W double prime. In other words, W double prime is accessible in 1 step from W. And since box A is true at W, we know that anything that is accessible in 1 step from W satisfies A, and that means that W double prime satisfies A. And that's exactly what we had to show. And that means that indeed this formula box A implies box A is true, is valid in an arbitrarily chosen transitive frame, and therefore in all transitive frames. Okay, so we know that box A implies box A is valid in all transitive frames. Now we want to show that it's valid only in transitive frames. Now, the strategy for this is going to be similar to the strategy that I used for reflexivity. Now, you could start by assuming that the formula is valid in a frame M, and then try and show somehow that that frame must then be transitive. But it's quite difficult to work that way. I think you will find you can try doing a proof that way. It's a perfectly reasonable way to go about the proof, but I think you will get into difficulties quite quickly, because somehow knowing that box A implies box A is valid in a frame doesn't really give you a handle on anything to kind of work with. Instead, I'm going to go the other way around, and to show that it's valid only in transitive frames, I'm going to assume that we have some arbitrary frame that is not transitive, and then I'll show that that formula must not be valid. And so I've got the freedom to come up with a counterexample. So it's going to be a bit easier to proceed this way. So let's take a frame which is not transitive, and we're going to show that the formula box A implies box A must then be not valid in that frame. Now, since the frame is not transitive, then there must be some worlds for which the principle of transitivity fails. So remember that transitivity says that anything you can get to by taking 2 steps in R, you can also get to by taking 1 step. So since M is not transitive, there must be some points where this principle fails. So that means that there must be worlds X, Y, and Z in W such that you can get from X to Y, and you can get from Y to Z. So you can get to Z in 2 steps from X, but you can't get from X to Z in 1 step. So I've slightly abused notation here by writing a formula negation in front of R. Technically, that's just my shorthand for saying RxZ is not true for in this case. So now I'm going to take an instance of the formula and which is not valid in the frame M, and I'm going to be free to choose a valuation, and I'm going to be free to choose a world in the frame for which the formula fails. So I'm going to take the formula A just to be a proposition. And the reason I'm doing that is because when something's not valid, it usually fails already for the propositional case, and because I'm free to choose the interpretation of my proposition, and I can kind of play various games. So I'm going to take the valuation of the proposition P to be the whole set of worlds except Z. So basically, the proposition P in my valuation is true at all worlds in the frame except for the world Z. Now, I want to show, I'm going to show that that box P implies box P, which is an instance of this formula, is not true at the world X. Now, that means I have to show that X makes box P true, but it does not make box P true. So first of all, why is box P true? This is actually quite similar to the thing we did, I think, for reflexivity. Box P is true at X because, well, P is true everywhere except Z, and we know that Z is not accessible in 1 step from X. We already know that by since we deduced that from the fact that M is not transitive. But it is true everywhere else, and that means that box P must be true at X. No matter where you can get to from X in 1 step, it can't include Z, and therefore, by definition of the valuation of P, P must be true at all those worlds. On the other hand, X does not satisfy box P. Why not? Because we know that we can get to the world Z in 2 steps. So we know that X does not satisfy box P because you can get to Y in 1 step, and Y does not satisfy box P, and Y does not satisfy box P because you can get to Z in 1 step from Y, and Z does not satisfy P. by construction. So it can't be the case that X satisfies box P, which means X satisfies the left-hand side of the implication, but not the right-hand side. So the formula is false at that world. Because it's false to that world, it's not valid in the frame. And since the only thing we assumed about the frame is that it's not transitive, we come up to the idea that that box A implies box A must be invalid in every non-transitive frame. In other words, the formula is valid only in frames that are transitive. So we now have our lemma saying box A implies box A is true in all transitive frames, and it's not true in any non-transitive frames. So by combining those two facts, we have that the formula box A implies box A is valid in a frame M, if and only if that frame, excuse me, is transitive. So again, we can actually say that the transitivity of a frame is actually defined by this axiom. We can kind of say that the validity of this axiom exactly captures the fact that the frame is transitive. If we take that formula as an axiom, then it is exactly the same thing as insisting that all our frames are transitive. And so, in fact, we can restrict to frames which are reflexive and transitive by taking the formulas box A implies A, which defines reflexivity, and box A implies box A, which defines transitivity as axioms. And actually, if you add those two axioms to modal logic as we defined it here, then that is a very popular modal logic called S4. That's one of the most famous modal logics. And yeah, and so it is modal logic where all frames are required to be both reflexive and transitive. And of course, if you want to think about relations that are reflexive and transitive, again, equality or non-strict inequality, so less than or equal to, are both relations that are both reflexive and transitive. Just to finish, as I think I said a little bit earlier, there's actually quite a lot of other properties of frames that can be defined by axioms or can be defined by a modal logic formula, and some that can't be defined. Now, in an examination situation, I would never ask you to show that a property of a frame cannot be defined by any formula, because that requires some quite sophisticated mathematical techniques which are outside the scope of this course. But if I gave you some property of a frame and a formula of modal logic and asked you to show that the condition that I gave on the frame was exactly equivalent to the validity of a certain formula in modal logic, that is very much the sort of thing that you might be asked to do in an exam. So it's good to get a little bit of practice with this. And so it's almost time for me to go. Thank you very much for your attention over these last 15 lectures. I hope you've enjoyed the logic part of the course, or that if you've not enjoyed it, then at least you've got something out of it. I really do believe that a thorough grounding in logic is really an essential part of the toolkit of any serious computer scientist, no matter what they go on to do. And I hope that you all will be extremely serious computer scientists, and so I'm glad that I've had this opportunity to teach you some logic, even as it were at a bit of a distance. So perhaps I will see you in the future, and perhaps not. Good luck for the exam, and good luck in the rest of your studies here at UCL. Take care. Hello again, everyone. Just before I leave you, I thought perhaps I would do one wee song, kind of intended for these tough times. Don't let 1 to 10. Frown to smile, upside down. Turn that frown upside down. Smile, sing, la 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 la, zing zing zing. Don't let it bother you when skies are gray. Learn to grin and take it on the chin. Everything will be okay. Don't let it bother you when skies are gray. Learn to grin and take it on the chin. Everything will be okay. Everything will be okay. Everything will be okay.